Welcome to Fuzzy Mathematics, the basics. In the previous lectures, we have talked about the properties of fuzzy operators, t-norms and s-norms. In this lecture, we will introduce several different fuzzy operators. First, Juddy operators, the maximum operation and the minimum operation. Secondly, the probabilistic sum and product. The probabilistic sum of A and B is A plus B minus A times B. Thirdly, the bounded sum and the bounded product. The bounded sum of A and B is the minimum of A plus B and 1. And the bounded product of A and B is the maximum of A plus B minus 1 and 0. Fourthly, the Einstein sum and Einstein product. The Einstein sum of A and B is A plus B over 1 plus A times B. And the Einstein product of A and B is A times B over 1 plus quantity 1 minus A times 1 minus B. Lastly, the drastic sum and the drastic product. The drastic sum of A and B is A if B equals 0. The drastic sum of A and B is B if A equals 0. Otherwise, it is 1. The drastic product of A and B is A if B equals 1. The drastic product of A and B is B if A equals 1. Otherwise, it is 0. The above operators are all fuzzy operators, where the maximum operation, the probabilistic sum, the bounded sum, the Einstein sum, the drastic sum are all s-norms, and the minimum operation, product, the bounded product, the Einstein product, and the drastic product are all t-norms. Maybe you have taken notice that these operators are presented in pairs. Yes, each pair is a pair of dual operators. Next, we will introduce the definition of dual operators. Let T be a t-norm, S be an s-norm. T and S are called a pair of dual operators. If the complement of S of A, B is equal to T of the complement of A and the complement of B for all AB in the closed interval from 0 to 1. This definition recalls the identities in De Morgan laws. But here there is only one identity. There should be two identities. Is something wrong? No. Actually, it makes no difference if you choose the other identity. The next theorem provides the equivalence of the two identities. Theorem 1. Let T and S be two fuzzy operators. Then the complement of S of A, B equals T of the complement of A and the complement of B, if and only if the complement of T of A, B equals S of the complement of A and the complement of B for all AB in the closed interval from 0 to 1. We need to prove that the following statements are true. First, let's prove the first statement. Suppose this statement is true. Replace A with the complement of A. Replace the B with the complement of B. Using the double negation law, the complement of A is the same as A, and the complement of B is the same as B. So it is going to be T of A, B. Take complementation of each side of this equality. Together with the double negation law, we have the complement of T of AB equals S of the complement of A and the complement of B for all AB in the closed interval from 0 to 1. Now we have proved the first statement. Similarly, we can prove the second statement. This completes the proof. Juddy operators: the maximum operation, the minimum operation, the probabilistic sum and product, the bounded sum and bounded product. Einstein sum and Einstein product, joustic sum and joustic product are all dual operators separately. Now we have made enough preparation for the definitions of generalized unions and generalized intersections of fuzzy sets. Let T be a T-norm, S be an S-norm. Suppose T and S are a pair of dual operators. Suppose A and B are fuzzy sets. The generalized union of A and B with respect to S-norm S is a fuzzy set denoted by this notation, where the membership function is as follows. The degree of membership of element X in the generalized union is S of A of X and B of X. The generalized intersection of A and B with respect to T-norm T is a fuzzy set denoted by this notation, where the membership function is as follows. The degree of membership of element X in the generalized intersection is T of A of X and B of X. By the definition of generalized unions and generalized intersections, we know that the properties of the generalized unions and the generalized intersections totally depend on the properties of the corresponding S-terms and T-norms. Because S-norm and T-norm are fuzzy operators, both of them have commutativity, associativity, and monotonicity. The generalized unions and generalized intersections have commutativity, associativity, and monotonicity. Considering the boundary conditions of T-norm and S-norm, the generalized unions and the generalized intersections have the corresponding boundary conditions. Since T and S are a pair of dual operators, then the corresponding generalized union and generalized intersection are also dual operations. To be specific, these properties are listed as follows. Theorem 2. Suppose T and S are a pair of dual operators. Then we have the following properties. First, commutative laws. The generalized union of A and B is the same as the generalized union of B and A. And the generalized intersection of A and B is the same as the generalized intersection of B and A. Secondly, associative laws. The generalized union of A and B union C is the same as A unions the generalized union of B and C. The generalized intersection of A and B intersects C is the same as A intersects the generalized intersection of B and C. Thirdly, monotonicity. If A1 is a subset of A2, B1 is a subset of B2, then the generalized union of A1 and B1 is a subset of the generalized union of A2 and B2. And the generalized intersection of A1 and B1 is a subset of the generalized intersection of A2 and B2. Fourthly, domination laws. The generalized union of A and the universal set is the universal set. The generalized intersection of A and the empty set is the empty set. Fifthly, identity laws. The generalized intersection of A and the universal set is A. The generalized union of A and the empty set is A. Lastly, De Morgan laws. The complement of the generalized union equals the generalized intersection of the complements. The complement of the generalized intersection equals the generalized union of the complements. We will prove the first De Morgan law. Suppose T is a T-norm, S is an S-norm. T and S are pair of dual operators. Suppose A and B are fuzzy sets. By the definition of complementation of fuzzy set, the complementation of the generalized union of X equals 1 minus the generalized union of X. By the definition of generalized union, the generalized union of A and B of X equals S of A of X and B of X. By the definition of complement of real number in the closed interval from 0 to 1, 1 minus this number is the complement of this number. By the duality of T-norm T and S-norm S, we have the complement of S of A of X and B of X equals T of the complement of A of X, the complement of B of X. By the definition of complement of real number in the closed interval from 0 to 1, the complement of A of X is the same as 1 minus A of X. The complement of B of X is the same as 1 minus B of X. By the definition of complement of fuzzy sets, 1 minus A of X is the same as the complement of A of X. 1 minus B of X is the same as the complement of B of X. By the definition of generalized intersection, it is going to be the generalized intersection of the complement of A and the complement of B of X. Now we have proved that the complement of a generalized union equals the generalized intersection of the complements. Similarly, we can prove that the complement of the generalized intersection equals the generalized union of the complements. This completes the proof. These properties justify the rationality of the generalized operations. We will end this lecture by a remark. If A and B are either 0 or 1, then these operators are equal to Jadi operators. That is, if the two sets A and B are crisp sets, then the generalized unions and the generalized intersections all degenerate to union and intersection between crisp sets. This also justifies the rationality of the generalized operations. Furthermore, if A and B are in the closed interval from 0 to 1, then apart from Jadi operators, none of the other operators has idempotent properties. So the idempotent laws do not hold in the corresponding generalized unions or generalized intersections. That's the end of this lecture and the end of this topic. Next time, we will move on to a new topic, class of fuzzy sets. Thank you.